if we remove everything from that, we will call it an aneroid. So an aneroid, now we're going to compare whatever pressure we're sensing with the pressure in space. So a manifold pressure gauge, typically the bellows are going to have nothing in them, or at least they like to say that. So it's an aneroid, and then we compare the pressure that's outside those bellows, how much is trying to crush the bellows with what's in them inside, and that's the pressure that we're reading. So that word aneroid is when we have a diaphragm or a bellows that essentially is a vacuum. Now they break the rules. Sometimes they put a known pressure with a known spring pressure and they mess with us. But that word aneroid, anytime you hear it, you should be thinking, oh, that's a diaphragm that is in a vacuum. There's nothing inside it. Joe.
Okay, never mind. I think.
Okay. So here's one with a diaphragm that looks like two bellows. It's a VSI, but there's a calibrated leak. And what they're doing is, on this one they put the calibrated leak. It's kind of weird, but they put it from the case to the static. And then we've got static pressure coming into the case. So they tried to draw a picture that says a VSI will always have a calibrated leak. I think you were asking, where do they put that at? Somebody was asking. Where's the calibrated leak? Well, the leak sometimes can be in or out of the bellows. Otherwise, what they'll do is they'll connect static to the inside of the bellows, and then the case itself will go out to static as well, and the calibrated leak will actually be from the case to out to the static port. So essentially, inside the bellows, you always have static pressure. Outside the bellows, you're going to have a changing pressure based on if you go up or you go down, and a calibrated leak to control how fast it can neutralize between inside the bellows and outside the bellows. Whew. I'm going to push pause because I think I know where I'm at, but I want to make sure. Yeah, okay, good. 4 slides. All right, solid state pressure sensing, we're going to use a piezoelectric. Piezo, if you remember, you put pressure on it, it produces a voltage. We read that voltage. So once we get into solid state, it's not an aneroid, it's not a bellows, it's pressure on a piezoelectric, what do they call those little things? Piezoelectric crystal is the word they like to use. They like to use the word crystal. In this one, they use the word material. So you can change material with crystal, and then you'll get all the answers right. They'll either call it a piezoelectric material or piezoelectric crystal. What was I trying to say? I gotta go back a slide. 10.6 in my book. 10.6. Oh, nearly all of the pressure information needed for engine, airframe, and flight instruments can be captured and/or calculated through the use of solid-state pressure sensors in combination with temperature sensors. But continued use of aneroid devices for comparisons involving absolute pressure is notable. So the reason that's there is if I had a piezoelectric sensor, is it going to be easy to compare the pressure of what I'm reading with space on one of these? Because I would have to make a case down here that's a vacuum that we would basically call an aneroid at that point, right? Because the pressure acting on here would have to be like space, and then I'm going to compare whatever I'm sending. Well, if I've got an aneroid anyway, why did I just turn it into an aneroid instrument? So all that to say, if we're comparing the pressure with an aneroid or the pressure of space or actual PSI-A, a lot of times they'll still stick with having an aneroid in there instead of going piezoelectric. Because the piezoelectric has to know, well, what pressure am I pushing against? How do I know what space is? It gets a little tricky. All right. name some instruments. We'll do 5. So I can tell you guys want to break. Give me one.
Oil pressure.
Oil pressure. Oil pressure. Is that going to be PSI A, PSI G? G. Yup. So it's going to compare what's around the gauge to the oil pressure coming to it. Manifold pressure. PSI A or PSI G? G, because we're comparing to space. Yup. All right. So oil manifold. I said A, didn't I? I'm sorry. A, PSI A, because we're comparing it to space. All right, 3 more. We're almost to break.
Is fuel flow?
Fuel, pressure. Give me a pressure, not a flow.
Fuel pressure.
Fuel pressure. PSI A or PSI G?
PSI G.
Pretty much PSI G, yup. So we can do that with a transducer. 2 more, we're down to 2.
Hydraulic.
Hydraulic pressure. That's not an engine, but PSI A or G?
G.
G. Okay, last one. Exhaust pressure. We were a turbine engine. Come on, guys. Turbine engines. PSI A or PSI G? Ooh, that's tricky. I bet that might be an A. I bet it's A. Yeah. We'd have to look. It's probably going to depend on the airframe that we're looking at, right? All right. One you didn't think of was suction pressure. Oh, suction pressure. Oh, man. Now, suction pressure gauges, it's on the screen. Come on, guys. Listed, if I had a suction pressure of 5 inches of mercury, it's funny, there's a lot of times we do them in PSI, but 5 inches of mercury, we'll say, or do I have it backwards? We do them in inches. That 5 is not a positive 5, so we're going to be a PSI G, but it's a negative, because our suction gauges are never going to put up their -2, -4, -6, -8, even though they should. To be technically correct, they should say negative. But they're just giving us a pressure difference of the basically static pressure. Our cabin typically is where we're at. Our cabin compared to what's in our suction line, what's the pressure difference? And they're saying, well, the difference is this many PSI. So that's why I would tend to say it should say negative, but they're just saying what's the difference in pressure from our suction to our, and it's typically just going to be where our cabin is. All right, turbines. Man, did I miscount? I know I saw a lady with a break. Turbines have similar. We have our pressure ratio. Yeah. Oh, that's what it was. The last slide before break. Pressure switches. Do you have a pressure switch? Pressure switches. There it is. What's the difference between a pressure gauge and a pressure switch? And then we can take a break once one of you smart people answers that.
One is on or off, and one is on a scale.
Exactly. Pressure switches, you're going to get an on or an off, a yes or a no. Gauge, you have a range, right? I got 8. So there we go. That's it. Take a break. Make it 10 minutes or 9 minutes. Come back at 10 to 2.
You said what is the difference between a pressure switch and a pressure
Gauge.
gauge?
So here's 2 pressure gauges.
Yep.
Here's 3 pressure switches. So what's the difference between these and that?
Because that can you turn that on and off. Pressure switch.
I'm not turning it on and off. I'm just giving an indication of, did I get high enough or not? So these will just open or close an electrical thing. This guy, he's not opening or closing anything, he's giving you an indication of pressure. No, if I hook one of these up into a light bulb, now I have an indicator. Say it's set at 30 PSI. If it gets above 30, the light bulb comes on, so it'll give me an indication of, am I above 30? Yes, or no. But it's a yes or no based on 1 point, or 1 pressure, if you will. I don't get a range with these. These aren't going to say, you're at 30, you're at 50, you're at 70. They're just going to say, yes, you crossed the threshold.
That was set for.
That we're set for, exactly.
Question about the manifold pressure. pressure.
Yes.
So manifold is, maximum manifold pressure you can have is whatever pressure you have.
Unless you have a turbo.
Yeah, okay, so that makes sense. So you're reading, the more pressure you're sucking, the Venturi effect thing. That's why you're reading less pressure, because you're sucking in more air, right?
We should say less. So when the engine's running, we typically aren't gonna read 29, we might read 24.
Yeah, because
Yeah,
there's,
we got an air filter and some other restrictions.
okay, so it's not due to the air sucking.
Yeah, it's just, it's because we went
You
from,
want it as high as possible.
if I wanted as much power as possible.
Power as possible.
Yep. Yeah, if I fly up to 10,000 feet and then I shut all my engines off and stop flying, I'm not gonna be 29 anymore because I'm at 10,000 feet. I think I'm 20 inches.
That makes sense, so it's just compared
Compared to space.
that makes sense, okay, cool.
The North Pole, you will have to tilt the sensor 9 works, you can check, and when an external angular mass attached to a spring,
172, and I like backed away when we heard that cracking from the. It actually was an O-ring breaking. Yeah.
You guys tore it apart?
Yeah, we tore it. We were working on tearing it
Well, then it
apart.
started leaking fluid.
Yeah, and Ryan said, this is not a good sign that this is leaking all that fluid. I'm like, yeah, me and Jordan heard it crack, and I promptly stepped back because I was like, I want nothing to do with this.
I don't know what that sound was. But
It was not a good sound.
The snowball hit the car.
Oh,
Correct.
yikes.
Someone cracked beans on the windshield.
No. Snowball joke. Whoops. Oops.
Nice.
I wonder who this is.
At least it wasn't a slug bug.
Are you giving a POH for the one for beach furniture?
Huh?
It says the POH.
You guys want the page?
POH.
Yeah, the POH.
Pilot's operating manual.
Handbook.
Yeah. Thanks.
Otherwise,
Page,
do
pilot's
a
operating
POH.
handbook.
Unless, of course, it's AFL,
Yeah.
Aren't you that I didn't say anything?
which I never understood the difference. So it's because nobody asked me.
You guys are looking forward to dash 9.
Okay, in order to get you guys out into the lab and almost the sunlight on time, everybody else is late. They're like, I'm taking my sunlight, but they won't learn as much. So I have in my hands a combination manifold pressure gauge and fuel pressure gauge. Manifold pressure, fuel pressure. Manifold pressure goes up to 35 inches. I don't know, in case it hiccups or something. I don't think I have a turbo on this aircraft, but you know. And fuel pressure is 0 to 12 psi. What type of pressure sensing gauge do you figure is inside here for each? Bourdon for what? Sounds right, but doesn't answer which one.
Would be A for manifold, G for fuel.
Not AG, what type? So Bourdon, diaphragm, piezoelectric,
Bourdon for the fuel pressure.
Bourdon for the fuel pressure, and a diaphragm and or bellows for the manifold pressure, yeah. We typically aren't gonna measure liquids with diaphragm and bellows, typically. So it's lower pressure and then air or air pressure. We don't want liquids to get stuck in our diaphragm. So yeah, probably a Bourdon tube on our fuel pressure and then a bellows / diaphragm on our manifold pressure on there. Pressure switches are not gauges, so you're not really gonna call it a diaphragm or a bellows. You could picture it like a diaphragm in there is usually what they have on our pressure switches is you got the whoa, that didn't work. You got the pressure coming in the bottom and it's held in place, and you've got a curved piece of metal, and if the pressure gets high enough, it'll go pop, it'll pop that the other direction, which trips the switch. That's typically the idea of what you have in there, but it could be anywhere in between that when it deflects a certain amount, it trips a switch. But we usually don't call pressure switches diaphragm or bellows because it's on or off. That's going to be reserved for pressure gauges. All right, so we're going to move over to gyros. You might have noticed I have been playing around with a bunch of different style gyros. We did deal with it slightly in general, and we're going to go over it a little bit more. The main thing is they like this word precession shows up on writtens and stuff. They also throw in a word procession, or I throw in the word every once in a while. Procession is not a thing, at least as far as gyros go. We always are going to be pre. Pre means it happened before, right? So gyroscopic precession is if I apply a force to a spinning gyro, the resultant motion will happen 90 degrees later. So where the pre comes from is before the resultant is where the force was applied. It was a precession. If you're into weddings, like Grant's into weddings. I don't know if you knew that or not.
Not just weddings.
I don't have all day to talk about it, but wedding videography. If you're into weddings, what do they call it when the brides and the grooms walk down the aisle, Grant?
The procession.
The what?
The procession.
Pre or pro?
I never.
See, it's an iffy. It's pre. Well, pro. Oh wait.
Is it before the session or is it for the session? I just say
Procession. There we go. That's why we were asking. I had to double check my notes. Procession is a certain order. Certain order. As in, the bride comes last. The groom comes first. It's a certain order as procession. So the bridal procession is a certain order. But gyroscopic precession is a before. So the force is applied before it's felt. So all that is trying to not confuse you. Is it gyroscopic procession? Is it a certain order? Well, kind of. But what you really need to know is that the force is applied before it is felt. So it's precession. It's not just an order, it's the order of precession. So anyway, all that to say, we call it gyroscopic precession. I'm going to do a brief explanation of it with a little bit of fun. You really don't need it for this class, but whenever you're talking about gyroscopes, it's fun to play with stuff, right? So the main thing for this class, and maybe I should have put that in yellow and red, is rigidity in space. So the main thing we care about for gyroscopes for instruments is the concept of rigidity in space. So if you have a gyroscope that's spinning, and usually we do it with a wheel, it will want to stay in that plane. It doesn't want to change the plane it's in. So I can do that with a little gyroscope. This is fun. And the reason we use this for instruments is I'm going to spin this up and get it going, and then I'm going to walk around it, and see how right now it's moving the way the red one is pointing. So if I were to, which way is north? That way. Okay, if I point the red one to the north, and actually I'll do it the other way around. If I point it this way, you guys are all looking at the red one, right? So if you're looking at the red one, you're looking north. If you're looking at the green one, you're looking south. So if I don't have the gyroscope spinning, all of a sudden which way north is a little bit hard to tell. But once I spin my gyroscope up, hopefully without breaking it. Ooh! And now I face it so that the red is pointing north. I can walk around it and I can tell I'm facing north. I'm facing south. I'm facing north. I'm facing south. Now it's moving slightly, right? That's because our bearings have drag, and that drag's going to mess it up. So as your bearings in your gyro instruments go, you start to have wandering indicators, just like this is slowly wandering. Ugh. But for the most part, if your bearings are perfect, it will stay in that plane in space forever. So we mount a gyro in the aircraft, and then we move around the gyro is how they work, right? So that's the idea behind when instruments we're talking is we move around the gyro. Now, just for the fun of it, if you're talking all the other gyroscopic principles that are probably more like Christina's and Ryan's classes, and I can't go past it without touching on it because it's so much fun. If I had a gyro going like this way around, if I were to say, we're going to keep it going that way for the fun of it, if I were to, right when it crosses that point here, if I were to tap it, and I'll spin it slow and tap it, ready, I tap it, what I'm doing is I'm imparting some energy, and as it goes by there, this is going to now start to want to go down because I tapped it down. Because I have a middle fulcrum, tapping down on this side is the same as tapping up on this side, right? So that's one concept, is if I tap down over here, this side wants to go up because I'm supporting it in the middle. The other concept is when I tap it down, ooh, that went weird. When I tap it down and it goes by, it's going to be felt, or if you were to watch this, if I could do it really good as it goes around, if I could ever so slightly tap it here, it's going to be, oh, I had it. It's going to be lowest at where Tiki is, 90 degrees later, until it gets a little bit off. But basically, and then that's going to start wandering, but it'll basically go the lowest to where Tiki is, and then it's starting to come back up. And you go, what makes it come back up the other side? Well, if I'm continually tapping on this side, part of what makes it want to come up after Tiki is I'm continually forcing this side here back up, which means it's going to be the highest back here at me, right? So there's a little bit of this teeter-totter action going on. But just for the fun of it, I made this today. This was fun. This one won't have any teeter-totter action going on because it's a string. So I'm going to spin this up this way to start with. Oh, safety glass in the front row, they say. So if I were to tap down on one of those nuts on this side, you could kind of picture, oh, I'm going to make a mess. You could kind of picture what would happen is it's not going to go down the lowest here, right? Because it takes a little bit to travel down as it comes around. So it's going to be, if I tap it here, it'll be at its lowest point over here in front. And if I were to just not have it spinning and I tap it down, it's going to go down and back up to this side, right? So you get that same effect in a spinning gyro, is it's going to go down, but once I crossed what's holding it up in the middle, it's going to want to come back up. Even if it was just one, it would do that same thing of it's going to go down to 90 degrees. Once I pass 90 degrees, it's actually coming back up the way the string is holding it on there. So if you watch the Smarter Everyday one that I may or may not have linked to this, I can't remember, it might show up on a later date, he'll talk about vectors and stuff. I did one of these with only one nut on here. It was kind of fun. We'll do it for just a sec. And it kind of works. It still goes down on one side and up on the other. The problem with doing it like this is the weight gets thrown all off. And if I try to change what's going on by tipping the drill, I can feel that weight in my hand. Whoa, 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 whoa. And I'm inputting a force into it. So here's what I'm going to do for you. This is fun. And you can play with this in lab. I recommend with safety glasses on. We haven't broke it yet, but, you know, it might happen. So I'm going to get it spinning. And I'm going to go vertical so you guys aren't in line with it anymore, right? So if I take my drill and turn it this way, that would be like putting a force on this nut here, right? And what you're going to see at the first second is if I do that, this nut's not going to come this way. Where's it going to come that way? Up at the top. So when I turn my drill that way, the top's actually going to come towards Tiki, and the bottom's going to come towards me, which means I'm going to move that so it doesn't hit my drill. So here we go, ready, whoa. Oops, hit the drill. So anyway, you can kind of play with this. It's probably hard for you all to see where you're at, but even when it's not a rigid gyro, the concept of it works. You know what, maybe I can do it this way better. So I go like this. I'll tip the top my way. So if I tip the top my way, it's like pushing down here. So Tiki's side should go down, my side should come up. Whoa, I hit the drill, it came up so high. Now, almost immediately it starts changing the exact angle that that happens on, because as I tip, I insert that inertia, and then if I stop rotating, I'm putting a force back the other way that turns it. So anyway, if you get some time in lab, there's a fun little deal that talks about how it acts 90 degrees after the force is applied. Or you could say the force is applied 90 degrees Oh, before it's actually felt. Well, how did I do that?
Broken.
I broke it. Okay. It was working so good, I gotta do it one more time. We can get this. Man!
Also a testament case to how strong lacing is.
Lacing is amazing, people. Okay, we're gonna get this. We're gonna get this. Here we go. Here we go. Oh yeah, there we go. You guys like it better when it's this way? Less chance of everybody getting hit. Alright. Whoa. Stop putting forces into it, Case. Alright. If I wanted to put the battery into that nut, what would I have to do? I'd have to do it up here, right? I'd have to pull the top this way. So if I actually just push the battery into the nut, that's going to put this one out and the top one in. Whoa. So it doesn't actually hit the nut. So I'll do that one again. Whoa. Anyway. Kind of fun. So, gyroscopic, pre-session, but really what we care about in this class is rigidity and space, but it's hard not to play with gyros. Keep going. In your books, 1053, it'll talk about it. How many accesses we secure our gyro by can make a difference on our instrument for what we're sensing with them. This particular one, the gyro is spinning, but this thing can only tip left or right on one axis, so I can't sense as much if it's that way. Where this one on the left, the gyro is spinning on these bearings, but this bearing will allow it to rotate this way, and this bearing allows it to go to the other way. And I'm not going to spend too much time on that, but if we put a double axis on it, we can sense more things. So if we have a artificial horizon, where am I at? There we go. If we have an artificial horizon, this gyro can both turn side to side and rotate along the longitudinal axis. So now I can sense two things. I can say, hey, am I turning side to side, and am I turning around? So it gives us two different things that we can sense. Is that indicator off? Seems like it should be flying sideways. Weird. So anyway, you can kind of play with those. I'll send this around the room, but more so, play with them in your own time if you get a chance. You can power a gyro two different ways. You can do it electrically. Our turn and bank indicator is electric. This one has electrical switches so that when the gyro turns sideways, there's a little bit of a delay action in this one. They put in there with a damping effect. But it can still get the electricity. So this one is an electrically driven gyro. This one is a pneumatic or an air-driven gyro. And if you look closely when this one goes around, you'll see there's little cuts in the side of the wheel. So basically we're going to use air pressure in this guy. We're going to feed it through the back, through the suction, right? So it's actually suction. Sucking it. We'll direct that across that gyro wheel on those cups, and that's what gets the gyro spinning in that one. So that's how we do a pneumatic gyro, which is what most of ours are. Alright. If there's only one ring, we'll call it a captive gyro. If there's two dimensions that can move it, we call it a free gyro. Maybe you should call it a more free gyro, because it's still only two dimensions, not three. But captive gyro, it only is allowed to move one direction, one pivot. A free gyro is free to move on two axes. So it's a little bit more free, so a free gyro is what we would call it. Okay, some of our captive gyros, even though it's a captive, it can only move on one direction, they'll cant it a little bit. So now I can move either sensing a yaw or a roll because I have my gyro canted. So some of our instruments are set up that way. It's a little bit more complicated than that, but that's all the deeper we kind of have to go in this class. Could be electric, could be pneumatic. Most of our turn and slip, I should say, indicators are a 2 minute. You'll notice on the bottom, it'll say either 2 minute or 4 minute. The idea is, if we are turning and that line lines up, whoa, that's curved, perfectly, you're in a turn that's gonna take you 2 minutes to go all the way around. All the way around is 360 degrees. So one of you that's good at math, if it's a 2 minute gyro, how many degrees are we moving every second? 3 degrees. 3 degrees per second. So you might have that on a written somewhere. They might be like, how many degrees per second are you turning in a 2 minute gyro? And you'd have to say 3 degrees. Now, some large aircraft, when I say large, fast, think fast aircraft, the faster you go in one direction, the longer it takes to turn around, because you have to change all that momentum to the opposite way, right? So large aircraft will often have a 4 minute turn and bank indicator. On a 4 minute turn and bank indicator, how many degrees per second would you be going? 1.5. So if it's 3 degrees for 2 minute, 1.5 degrees for a 4 minute. Now, that's what we call a standard rate turn. So whatever one they have in your aircraft, if you want to do a turn at standard rate for that aircraft, you got to line it up. Now, in a 2 minute one, if I were to line that up, so 1/2 is covering it. Well, in theory, now I'm at a half rate turn. So now I have a 4 minute turn. It'll take me 4 minutes to do a complete 360. If I switch to the other style instrument, because some of them just have, and they'll call this the dog house. Can anybody tell me why they call that the dog house? Oh, good job. You guys are paying attention. Very nice. If you've never had a dog at home that slept outside, did I show you they're not dogs, they're doodle videos yet? Yes. Yeah. See, I don't have a dog house anymore. That'd have to be, well, anyway. Marcy? Okay. So they'll call that the dog house. So in prepware, when it says, if the needle is lined up with the dog house at a 2 minute standard rate turn, gyro, how many degrees are you turning per second? You'd say, I'm turning 3 degrees per second, right? So the dog house. Okay, if we go to our turn coordinator, notice we have a little bit different terminology, and the problem is the manufacturers will trade back and forth. They used to call this a turn and slip indicator, and they call this one a turn coordinator. They basically, for you guys, for mechanics, they basically do the same thing. Pilots, they're a little fancier, but for you mechanics, they basically do the same thing. The turn and slip, this is the slip. It's the little ball and the thing. If I am not using my rudders right and it's trying to throw me against a wall, that little ball will get thrown out to the side. So that's the slip indicator. The turn indicator is the gyro portion. Same over here, turn coordinator, it still has a slip, so technically we should call that the turn and slip coordinator, but they don't, they just call it turn coordinator. If you have the aircraft wings, a standard rate turn is when the aircraft wing is lined up with the little line. That'd be a standard rate turn in that. What's a little bit different with these guys is this does not tell you your bank angle on your wings. Don't think that. Now, if you're coordinated, if the ball is in the middle, it pretty much tells you the bank angle on your wings. Because if you're coordinated with banked wings, you're turning, aren't you? Yeah. But if you're not coordinated, it doesn't work that way. To prove the point, we come back over here. We're going to spin up our turn coordinator. Good, I wired it the right way this time. I got to give it a minute to warm up. The flag's going away. Okay, I'm flying level, right? As I start my bank, the airplane will start turning before me. Once I'm into my bank, if I hold it long enough and I just hold it there, notice the wings go basically back level with the ground that's indicated here. Because it's like, hey, you're not rolling right now. So our turn coordinators, they do measure if you're starting a roll or or stopping a roll, because that makes them a little bit more accurate than the old style. The old style don't tell you if you're starting a roll or stopping a roll. They just tell you if you're turning around in this way. So this is a little bit hard to do with you all there, but you can do this when you get into the lab. Is if I'm like Randall and I'm slipping into a landing, so I'm flying the airplane, I'm flying straight and I'm slipping into a landing, I got my wings all crooked, but it's like, hey, you're flying level, Randall. No, we can't do that, because that doesn't tell us that. That just tells us I'm not continuing to increase. Now, if I'm flying level and I'm flying in a circle, oh, now it's saying I'm making a turn, right? Notice my wings are level while I'm doing this, but that airplane's wings went way unlevel. And the reason is, this guy is not telling you what your wings are doing. They're telling you, are you turning in space, or how fast are you changing your bank? So, this guy up here, when we kick it on, he's the one that tells us where our wings are in space. It compares the gyro that stays stable in space, and you're looking at it, and as you move around the gyro, the airplane's wings move. But our turn coordinator is telling us, are we doing this, or are we starting or stopping a turn? So they want you to know that.
With the G1000 system, you can reboot your instruments, but you have to make sure that you're flying straight and level so that it calibrates correctly.
Yeah, some of the digital instruments, if you start them up and you're on like an angle like that, so let's say you're flying and your aircraft's on an angle, when it first starts up, it's like, hey, where's level? Well, okay, I'm level. And if you were in a curve and then you level off, it'll be like, the horizon's not where I thought it was. So some of them, when they're booting up, basically they measure with some gyros, and we'll show you how, but they measure and they're like, okay, we're stable. Okay, that must be down. But if that's not down when it fires up, well, you got some problems. So, yeah. That's our attitude indicator, aka artificial horizon on the digital version is what he's talking. Even our pneumatic powered ones have a feature like that in it. We're not going to go real deep. If you look at it in your book, it'll talk about it. But basically, if you were to take this instrument and if you were to fly not coordinated, if you're flying with your wings like this, but you're flying straight for a really long time, so that gyro is going to have your wings, but it will slowly actually get back to where, I said that backwards, your wings are leveled off. If you have your wings in a bank and you are coordinated, so all the force is down on that angle in the aircraft, right, you're doing circles, the wings will slowly level themselves out. So kind of like your head will mess with you. This guy, if you stay in a bank long enough, it'll get messed up too. Because it's basically setting the horizon almost like your VSI does. It's a really long delay, but it puts the bottom of the horizon at wherever straight down is for the G's it's feeling. So it's I think a couple minute delay, a minute or two delay is how long it takes. But it will mess you up if you are just flying circle long enough. You can get the wings to go back level in your circle.
It's just a wild thought, but is that why most holding patterns are oval versus just a circle?
Correct. Yeah, if you were flying a circle holding pattern, eventually your wings would show your level when you're in a turn.
Wow. Fascinating.
Good insight.
How do you keep that from like not messing itself up?
It's long delays. The idea would be kind of like Job was saying, you're not going to just keep flying with your wings banked for a long time. You're going to turn, then you're going to level off. Then you're going to fly level for a while. Then you're going to turn, you're going to level off. Fly level for a while. Turn, level off.
If this isn't level, how do you know where level is if you're like...
So if you're coordinated, and if these wings are level, you're not turning. So by comparing the two, if your wings are level on this guy, and it's working, this guy's not, he's got a red flag. If your wings are level, you are not turning. So if this guy tells you if you're turning, the other one just tells you where your nose is pointed in relation to space.
On the next slide, the bottom right, sorry, yeah, that one. At the bottom right, it says pull to cage. What does that mean?
Oh, good question. I think it's in a slide or two. But basically, you guys took my gyro, I gave it to you. Our gyros have the gyro in there, and you kind of hear it when I do this. No, you can't. I did it a second ago. There it is. Ooh, ah, ooh, ah, ooh, ah. That can't be good on the insides of this thing, right? Very sensitive instrument. We don't want it like bouncing off. Oh, ah, ooh, oh, it's painful just to hear it. So if you were gonna ship this somewhere, what you would do is you would pull to cage, and it'll put a pin in and basically lock that gyro in space. So in prepware, there's some questions about caging the gyro, and that's exactly what it is you can basically pin that gyro so it doesn't move, so that if you're shipping it, it's not going ooh, ah, ah, oh, ah, oh. Off the stops. There's dust or something in here. Off the stops. The other reason you might want to cage a gyro is if you're an acrobatics guy, and you're going to be like, wah, flipping through space. You don't want your gyro trying to figure out where you're at. So before they do crazy acrobatics, a lot of times if they have old style, they'll cage their gyro so it just locks in space while they're flipping all around. Because otherwise it's gonna get so confused. Because the gyros on those, you only get about 30 degrees, right, of indication. If you push it past 30, you've hit a stop, and now we're not doing anything anymore. So when they're doing crazy acrobatics, they are not using the gyro to know where they're at. They're looking out the wing to say, hey, where am I at relationship to the ground? You don't do acrobatics. IFR. Now, if you have electronic, and we'll get to electronic gyros shortly, now we have a whole other thing. An electronic gyro doesn't really matter. It can figure it out. All right, pull the cage. All right, the other one is, next slide, vacuum. So that tells you this is a vacuum-powered gyro. Some of them will tell you electric. Usually if they don't say vacuum, they're electric, just a FYI. But they like to say that vacuum. So this guy is in a left bank, and he looks like he's not diving or climbing. Now when I take a picture like this and put it up there, we go, wait, his wings are level though. Well, what's happening is the aircraft is moving around. This blue-gray line is always going to be level with the earth. And as we move our airplane left and right, we are going to move so that as a pilot, when I'm looking at it, it looks like the ground's moving, but it's actually I'm moving across that. It's hard to do on a PowerPoint though. So there we go. That's what would actually be happening, right? The ground is still level with the real world, but he's sitting inside the airplane going, oh, I'm in a left bank. Joe.
I just thought of a second reason for the oval holding patterns.
Yeah?
The wind drift on a continuous circle would be pretty wild, so that inbound leg allows you to reestablish position. So
There
I
you
guess
go.
those two reasons are
Yeah.
wise or not. If you're in IMC.
We'd probably get sick if you were like constantly going in circle too. You'd come out of the holding pattern and you'd think you're in a death spiral.
Like, whole.
All right, so that's a picture. That's what's actually happening with the instrument, right? Bad picture, good picture. All right, technically that's going on. Okay, how about this guy? Is he climbing or descending? How do you know? Yeah, we can't trust that instrument. We got a flag. I gotcha. That's right, it's flagged. That instrument doesn't work. We don't know if he's on the ground or what happened, but we're not trusting what it says. Okay. There's the slide with cage, so good job, Shane, asking that. 2 slides early.
Okay, so that attitude indicator, seems like there's 2 planes that are being measured. Is that?
Yeah,
Is that
you got,
standard?
you got roll and pitch. Yep. Yeah, it won't catch yaw. Yaw is not going to be a thing. And that's back to the gyro. Is that going to be a free or a, what's the other type? Free gyro? Less free.
That's free.
What was the less free? one?
Captive.
Captive. Is this going to be a free or a captive gyro? Free. This is a free because there's 2 rotations it can sense. It can sense up and down, and it can sense roll. A captive gyro would only be able to sense one of those. Now, if you mount it on an angle, it'll give you one indication. It might be able to instruments use a gyro that we're staring at, other than the attitude indicator? Heading, yeah, so my directional gyro. So, our directional gyro, the FAA in general considers 3 degrees of drift within any 15-minute period acceptable. So if you're flying for 15 minutes, they're saying this thing can be up to 3 degrees off and you're fine. If after 15 minutes you're 5 degrees off, it's saying unacceptable. Reality is, they drift a lot. So there's a lot of heading indicators that are in airplanes that are not acceptable to the FAA. But that is the official FAA version. The reason for that is, say you're flying 120 mile an hour, which we say knots, 120 mile an hour in a certain direction. We'll draw, this is terrible. We'll draw a map, and you're here, and you're doing 120 knots in that direction, and you're gonna fly for an hour. You're gonna fly for an hour. If my guy ends up being 10 degrees off after an hour, we can do some math and say we averaged 5 degrees off. This is gonna be really rough math, it's gonna be a curve, but you get the idea. So, if we said we were 5 degrees off course, can anybody tell me how far off of my destination would I be if I averaged 5 degrees off course? Now, it's a rough math average, but. Anybody? You pilot type? You want to try to guess? Now come. So the math is on 60 miles, which in our case would be a half hour, 1 degree off course is 1 mile off course. So if we're doing it for 120 miles, you can do the math a bunch of different ways, but we could say maybe we'll change it back to 10 degrees off, but use the 1 in 60 rule. So we got to split it in half somewhere, but 10 degrees off course would give me a 10 miles off. Because I'd either be 5 miles off here and another 5 off here, depends on which way you want to do it. But we'd be roughly 10 miles off course with a 10-degree heading error after only 1 hour. So that's why the FAA says, well, you better be accurate to within 3 degrees every 15 minutes, otherwise you're going to be way off course. If you're like 3 miles off course and you don't have GPS, you'll be like, where'd that airport go? I don't know if you guys have done that, but yeah, I've done that. Cheddar.
That heading indicator has a 0 on the wrong dash.
Yeah, the FAA's got some funny pictures, don't they? They got, yeah, where should the 0 be? The funny is 33, 34, 35, 36 should be 0. Yeah. Yeah. I actually had it on an exam once. Yeah, we had to correct it. FAA. Did we ever tell you that there's jobs available for technical drawers that understand the technical stuff?
It's like AI made that.
I don't know. So, the solution to this is every 5 minutes, 15 minutes, 10 minutes, depending on what aircraft company you're working for, flying company, is you're going to go to that heading indicator and you're going to look at your compass and you're going to say, okay, I'm flying north. All right, let me correct. Yep, I'm flying north. And then that thing moves a little bit and 10 minutes later, oh, check my compass, I'm flying north. Yep, I'm flying. So you actually have to manually go adjust that every 5, 10 minutes to make sure you're heading on the right course. All right, did you say something, Marcy? No? Is Amanda?
Yeah. What? Why are they learning this? Like,
Yeah, because you are responsible for installing that and uninstalling that, and it runs off your vacuum system. And if you install it wrong, you're going to kill somebody because they're not going to find their airport. Or compasses are pretty cool, but when you start turning with a compass, there's lead and there's lag and they swing and they're terrible. So they are instruments in the aircraft that you're certified to work on the outside of the box, so you need to know how they work.
so we're only allowed to do one test, like just a leak test.
The leak test.
So how are we supposed to, you can adjust these things on the outside, is what you're saying.
The pilots and or you will set it. So like as a mechanic, if you wanted to check your drift, maybe you're a pilot mechanic, maybe you're you're sitting there for 15 minutes and you're making sure it doesn't move anywhere. It's gonna be a little bit weirder. That one's gonna be more for a pilot. They're like, hey, I'm getting 10 degrees of drift every 15 minutes. You're gonna be like, yeah, I need to install a new DG, a new attitude indicator for you, because that's outside of what the FAA says you should get. So that's the kind of reason we're learning this.
You can say that as mechanics, we're supposed to know how the instruments correctly work, so that if it doesn't, we can have it.
That'd be a good way to put it.
And go get fixed.
You should know how the instruments work correctly, so if they're not, you know to send it in, yeah. Alright, we're gonna switch from regular gyros, which the principle is rigidity in space, right? Primary principle of instruments, gyros, rigidity in space, to solid state gyros. Now, under solid state gyros, they'll sometimes call them a RLG, which is a ring laser gyro, and sometimes they'll call it a MEMS gyro. RLG or laser gyros and MEMS are two different things. So we're going to cover RLG first. Basically, a RLG gyro has two lasers inside, and it shoots, basically it goes ready, set, go! And it shoots the lasers, and they go around off the mirrors, and they come back, and it can measure who is fastest, who got back first. So, on this picture here, what you see is when they said go, it was aligned here, but after they said go, they had rotated the device slightly. So the time it took for the laser to run that circuit, which it's unfathomable to me because light travels at, what did we say? 300,000 meters per second. And they're gonna measure which one got back faster around that little 1 centimeter course. But apparently it works. So they say go, and then they start turning that thing. And in this picture, the blue laser, if you will, got back first. Because if you look at it, it didn't have to travel as far, right? Light travels at a certain speed. It didn't travel as far. It got back first, where the red laser had to travel further, which at a set speed, it took it more time. So an RLG gyro will look at that and say, oh, you must have spun in space a little bit, and it's sensitive enough to measure that and realize you spun. So that's a RLG gyro. I don't think they're as common anymore. I believe they'll use those with more like missiles and crazy stuff, or if the GPS goes down, it'll measure, you know, it's a gyro in there for, I can still find my target an hour later without GPS because I've got these gyros in here. Pretty cool stuff. But they're there, older technology. Nowadays, MEMS gyros are what we do. Here's a little MEMS gyro. This baffles my mind as well. Compared to a quarter, they're pretty small. They got a lot smaller, and weight is everything in aviation. So instead of having a big, heavy gyro like you guys are passing around, why not use this little tiny thing that's smaller than a quarter? This is what all your phones have on them. So when you shake your phone, it can sense it. They got MEMS gyros typically in 3 dimensions. But we got a little video. I'm going to start the video for you. You're going to get the basic idea, and if you want to watch it in your own time, you can later. But basically, a MEMS gyro is going to sense movement, and then it's going to translate those shocks or those movements into, if I start a turn and stop a turn, they're so sensitive they know that you rotate a certain distance. Pretty cool stuff. So, I'm only going to run a couple minutes of this.
The North Pole, you will
And then if you want to watch it on your own, you can, but it gives you an idea.
Hello, Dan Nedelkovsky here from howtomechatronics.com. In this tutorial, we will learn how the MEMS accelerometer, gyroscope and magnetometer work and how to use them with the Arduino board. Also, with the processing development environment, we will make some practical applications using the sensors. First, let's briefly explain how each of these microelectromechanical systems or MEMS sensor work. We will start with the accelerometer. It measures acceleration by measuring change in capacitance. Its microstructure looks something like this. It has a mass attached to a spring, which is confined to move along one direction and fixed outer plates. So when an acceleration in the particular direction will be applied, the mass will move and the capacitance between the plates and the mass will change. This change in capacitance will be measured, processed, and it will correspond to a particular acceleration value. Next is the gyroscope, which measures angular rate using the Coriolis effect when a mass is moving in a particular direction with a particular velocity, and when an external angular rate will be applied, as shown with the green arrow, a force will occur, as shown with the blue arrow, which will cause perpendicular displacement of the mass. So, similar to the accelerometer, this displacement will cause change in capacitance, which will be measured, processed, and it will correspond to a particular angular rate. The microstructure of the gyroscope looks something like this: a mass that is constantly moving or oscillating, and when an external angular rate will be applied, a flexible part of the mass would move and make the perpendicular displacement. Okay, now let's explain how the magnetometer works.
How do they do that inside that little box that's, I'm stuck. Where am I pointing at?
Will cause change in
How do they do that inside that little box? Just magic. Amazing. And it's not even measuring where you're at in space, it's measuring the acceleration of when you twist and stop twisting, and somehow it's crazy more accurate than our actual gyros are. So anyway, what you need to know is MEMS gyro, that's what they're doing. They got masses and floating and capacitance changes inside that little tiny thing. And they'll usually have them in multiple directions, where a ring laser gyro is actually shooting a laser around and measuring time. But,
What does MEMS stand for again?
I don't know. I think it's something to do with mass, I don't know, somebody have to look it up.
Culture.
They didn't ask us that one. Alright, yeah. Okay, so we're gonna flip over to, it's 2:30, we're almost done. We're on 67 of 88, and the last three are almost nothing. Temperature measuring. So we can measure a couple different ways. We already talked about the board on tube, right? So we're gonna deal with a couple of the other ones that are more like bimetal. So a bimetal is you got two different metals fused together, and one wants to expand more when heated than the other one. So it's either gonna open up that little spring or close the spring. That's what most of your thermometers are made out of. Now, the bimetal's probably not in here. They do some warping and they got it running down here. And it's a bimetal that's spun inside there. And as those bimetals warp, it's still gonna spin your indicator. But, so most of your temperature gauges that have just a flat face on them like that, most of those are gonna be a bimetal. On your exam, we'll ask you stuff like, you have two metals fused together. One expands faster than the other. What type of thermometer is this? And you'd have to know it's a bimetal. Because if I said you have two metals fused together, where did your brains go maybe? Thermocouple, right? Because in our thermocouple systems, it's not thermocouple systems. In our thermocouple systems, if we have two metals fused together, those aren't fused, they're stuck. Two metals fused together, it'll create a voltage, and we can measure the voltage. Did you guys do this? I'm starting to have that time of year. Did we measure turbine rings with you guys yet? Ooh, fun, that'll be fun, it's power plant. So this is a ring off a turbine, and each one of these is a thermocouple that's sensing the turbine temperature. And the way it senses it is there's two metals that are fused together, and because there's two different metals fused together, the voltage created across essentially the joint is going to be able to be read on a voltmeter, and we can read the temperature by reading voltage. So that's a thermal couple, and we'll come back to that in a second. So, bimetal is two fused together, one expands more than the other, it moves a mechanical spring to give you an indication. And one other type is electrical resistance. Electrical resistance means we have a thermistor, right? As a change of temperature, thermal. The resistance changes. So if we change the resistance of a sensitive bulb, that's going to change the current flow through here and make that magnet stronger or less strong than what's on our set side, and our indicator is going to point and say, hey, I'm either hotter or I'm colder. So multiple different ways to sense temperatures. We can do board on tube with refrigerants. We can do electrical temperature measuring with resistance. We can do thermocouples, and all kinds of fun we can have. Did we talk about ratio meters and Wheatstone bridges? No. Okay. It's that time of year. That was one of the last classes you'll have. It's like, I feel like we did that already. So a ratio meter is going to compare the resistance on this side, it's our sensitive element with a thermistor, to the resistance on this side. That one's going to be a set resistance. It's not going to change with temperature because it's inside the instrument. So if this resistance were to go down, I'm going to have more current coming through this side. It's going to change the magnetism here, and it's going to changing the magnetism is going to change where my ratio meter points. So a ratio meter will always use a thermistor or at least a changing resistance to give us an indication. A Wheatstone bridge does it a little bit differently in that we've got our thermistor out here, and a Wheatstone bridge basically still has two set resistances, and inside here is going to be very, very similar to what you're seeing there. We're going to call it a, let me find it a minute, was it on the slide? Might not be on the slide. A ratio meter, might even just call it a voltmeter. These resistances will stay the same, and this resistance along that path is going to change. So, if I have a set resistance of 5 ohms here and 5 ohms here, and let's say this one's 5 ohms, and let's say at 70 degrees out, this one's 5 ohms. Now I've got 5 ohms everywhere. The voltage drop, if I got 14 volts from here to here, the voltage drop across this side would be the same as this side, which means the voltage from this point to this point would be 0 volts, which means my needle would point straight up with 0 volts, right? But if I come over here and I change this resistance to 2 ohms, because it's a thermistor and I either got it cold or I got it hot, now if I have 14 volts dropping across those two, I'm going to have a different voltage at this point than I'm going to have at this one. So let's do the math real quick. 14 volts across this side. If it's 5 and 5, I'm going to drop the same voltage on each, right? So you could say 7 volts here, 7 volts there. On this side, if I've got 5 ohms and 2 ohms, oh man, I got to do a different kind of math. I'd have to take 14 volts. Oh good, we got lucky. 14 volts divided by 7 ohms. 14 divided by 7 is going to give me how many amps? Now, the digits are probably a little off, right? We're probably not dealing with actually 2 amps. But I would have, we'll say 2 amps going through there. So 2 amps times 5 ohms, I'm going to have 10 voltage drop here and a 4 voltage drop there. So if I compare this point and this point in that particular drawing, I would have had what would have been kind of 7 compared to that one, and I have more pressure. It's more positive here than it is there, right? So this, whether you want to call it a voltmeter or ratio meter, would say, hey, I've got more positive on the top, and I'm going to give you that. So it's not that you have to do that math all the time. There's one prepware question that'll ask you, if your resistor burns open or goes infinite resistance, what is going to happen to your Wheatstone bridge? And it's worded really bad. The answer they would want you to know is they would say, if this is open and I have no flow through here, I would have all 14 volts here, so this one's more positive and this one's more negative, and it would go down to a negative reading. It's a really weird question I don't like. But when you see that shape with 2 set resistors, controlled, and then a thermistor. The calibrated one just lets us tweak it a little bit, but they call this whole setup here a Wheatstone bridge, as opposed to a ratio meter is, well, we're just comparing the sides. And we don't want to get too deep. The resistor type, with a sensitive resistor, either one of those has a resistor, they usually work to about 300 degrees. They want you to know that, because if you get beyond 300 degrees, we're going to start overheating our thermistors, our resistors, they're going to start burning up and cause problems. So anything over 300 degrees, we're usually going to transfer over to a thermocouple style device. So thermocouples, sensing applications, typically over 300 degrees. Now, they do work colder, but anything over 300 is pretty much always going to be a thermocouple device. And there's a couple different styles of them. We have one style is what we call a gasket or a ring type. They can make that thermocouple in the shape of a ring and maybe screw your spark plug through it. Or a bayonet type. A bayonet type, well, it looks like a bayonet. It sticks in somewhere, right? So you got ring type, you got bayonet type. The thing on the tests that will end up getting you is if you have really, really high temperatures, you're going to want to use metals that can deal with that. So on super high temps, like exhaust gas temperature or turbine temps, you're going to use and the way I remember it is the expensive metals. You're going to use alumel and chromel. If you want an expensive car, you get a chrome, right? At least back in the 80s. Chrome. If you're using regular temperature, not quite as hot, still above 300, but more like cylinder head temperatures, oil temps, stuff like that. You might just use iron with constant tan or copper with constant tan. The constant tan is the constant, get it? Constant. So you'll always have one of the materials is constant tan. The other material will either be iron or copper. What's more expensive, iron and copper or chrome? Chrome. So we're going to use the chrome on our super high temps, like our super expensive jets. So that's how you remember it. Your chromel, alumel, expensive stuff. Iron or copper with constant tan, not as hot. Oh yeah, Joe, did you have a question?
Yes, sir. So this electrical resistance thermometer and the thermocouple, are those both two types of bimetal temperature measurement?
No, this is not a bimetal because, I mean, technically we could make it all with copper insulation, right? This is using a thermistor, so it's a heat-sensitive resistor. So the bimetal is going to be a thermocouple. We're using two metals, but technically, if you want to use the word bimetal temperature sensing, they're going to be liking this style, where it's two metals fused together, one warps, expands more than the other, and it warps it over. So they like to call these ones bimetals. Technically,
so
a thermal.
It's kind of similar in action to a Bordock tube, somewhat.
Yeah, the deflection is what causes the indication.
Okay, that
Yep.
makes sense.
Where on a thermocouple, there's no deflection happening. We're creating a voltage by having two dissimilar metals. The other thing they like you to know, I think we deal with it in power plant, not necessarily airframe, but I'll give you a little cheater, is wherever you're sensing the temperature, we'll call the hot connection. It's where the two metals is hot. Makes sense, right? So if they want to know where the cold connection is inside your gauge, they'll actually have where those two metals are reconnected. Because if you really get deep, and we'll deal with it in power plant, there's an electric flow, there's a circuit going through, in the old ones at least. So the cold connection is in the meter itself. The hot connection is where you're sensing the temperature. Because they're super sensitive, super sensitive, we're talking thousandths of a volt is what we're making with these things. We're not making much power at all. Because they're super sensitive, especially old school, the wires that we make them out of will still be whatever material we joined together. So the wire will be like constant tan, and the other wire will be copper or iron, or alumel, chromel. They've pretty much figured out how to get away from that, but there are still prepware questions around that. Let's say you had a bad connection here. You wouldn't be allowed to just cut it and put a new ring terminal on because they're super, super sensitive to resistances. And by cutting that much wire out of just the one side, you're going to change the resistance and it's going to mess with the gauge reading. So they want you to know you're not allowed to cut thermocouple wires. Now there are some that we can start to do that on. But the general rule of thumb is on a thermocouple, you're not going to cut the wire. You're going to buy a thermocouple with a wire the right length to go wherever it's got to go. If you want to do a deeper dive on your own, you can look up the Seebeck effect. It's really deep. It's kind of funny. Talks about the cold junction. But yeah, if you look at your CHT with a thermocouple, if it's 80 degrees out, it'll still read 80 degrees. And you're like, how does that work? Because it's not any warmer than in my cabin. Anyway, Seebeck effect. It's really weird. They still read temperature, but we're not going to go that deep. On a turbine engine, and this is more engine, we're creating a voltage with a thermocouple, right? So if we were to stack up 10 of these in a row, and basically what we're going to do is we're going to average that voltage. So whatever the average voltage is going to come down our wire. It's usually going to go through an amplifier to go to the gauge and say, hey, this is what your voltage, your temperature is producing. So if just one of those goes bad, while your gauge still works, it's just one of them dropped out.
So kind of a funny story. When I was little, my dad did AC, you know?
Yep.
And I drew up this whole design when I was a little kid of this air conditioner that would be basically a heat exchanger of thermocouples that would be taking the heat, generating electricity to power itself.
It would work. It would work.
My dad told me it was garbage.
The problem is, we're talking thousandths of a volt. So
Well, just stack up like a bunch of
it
them.
would be. I've done similar, I've done the math, but you'd have like you'd have like a $200,000 air conditioner that'll run on its own, right? But at 5% a year on 200,000, you're at 40 grand a year. You could pay for utilities instead, and it doesn't work mathematically. But you are right. You are right. You could run.
If only I owned a thermocouple.
Oh, man, almost 3. Tell you what, I'm not gonna have a lot of lecture time left if I give you a break now. I think I only got a couple slides. Let me look. We're just gonna rush through this. That's a bad spot for a break. All right. Tachometers are pretty cool. It's back to engines, but is it airframe? Is it engine? Basically anything that shows up in the cabin starts falling kind of on airframe, so we start blurring those lines a little bit, right? So a tachometer, we can have a couple different styles. We've got a cable coming from the engine. When the engine runs, it spins the cable. The cable spins a gear, and that spins a thing that the faster you spin it, the more gyroscopic force.
Centrifugal force.
Centrifugal force, that's the word. The more centrifugal force we have, because there's a spring, so the faster I spin it, the more those weights want to go out, which means it basically is going to pull this in, which changes the angle and gives us an RPM. So that is going to be the simplified version of what we call fly weight. Those weights that are spinning around the outside are fly weights, we call it. That's one way to do a tachometer. Very mechanical, a lot of things that can go wrong. They have basically since switched to a magnetic drag cup. In a magnetic drag cup, we still have a cable on the engine that's spinning and will run into the cockpit. It will spin a magnet. That magnet sits inside an aluminum cup. And the reason they call it a drag cup is a magnet will produce eddy current in aluminum still, right? You guys remember that from Maths and Pros, was it, or inspection? So aluminum still has eddy currents even though you can't magnetize it. So the eddy current that tries to get established, that aluminum cup will try to chase the magnet, but it only goes kind of so far because there's a spring resistance on it. So the faster you spin it, the more the cup will try to chase the magnet, and that will give you an RPM. We have one of these, I think. Did I leave it out or did I put it down below? Shoot. I think I have it down below. have one of those that we'll go over in power plant class that you can look at the inside and see the drag cup. But it's an interesting concept that a magnet spinning inside an aluminum cup will drag the cup, try to drag it with it, so we call it a drag cup. So that's another type of tachometer that we use. And in power plant, we'll actually talk about a third type. The third type has where the engine runs basically a little alternator. It's an AC generator, and it'll produce AC power at whatever frequency. You can do all the math, right? And then they run the 3 wires over to your tachometer in the cockpit, and inside the cockpit they have another electric motor that's going to run at almost the same frequency, right? It lags it just a little bit, and it's running at almost the same frequency back into a drag cup, just like the cable driven, and then that drag cup will give us an indication. So that's kind of a remote sensing version. In power plant class, we'll go deeper into that one and talk about the phases and how it works. But so there's 3 different ways we can do tachometers. One is the flyweight, the next one is the drag cup, and the last one is what they call a tach generator. It's generating a voltage at a certain frequency. We really don't care about the voltage, we care about the frequency. As the frequency goes up, this motor will run faster, faster frequency back into a drag cup tachometer to tell us, or drag cup indicator to tell us, hey, what RPM is our engine running at? Alright, we're dealing with very sensitive equipment, right? Very sensitive instruments. The housings look rugged, but the insides are not. A lot of times the case of these is going to be something that'll interrupt any magnetic forces. So you'd kind of say, I think the prepware even says, the cases often are steel. I'm like, oh, don't say that, because about 5 days later we're going to talk about our compasses and how we never put anything that's ferrous anywhere near our instruments, because it'll mess up our compasses. So usually the cases are made out of aluminum. They're made out of something that will keep the magnetic waves from going in there. But yeah, if they get a crack in them, we're not allowed in. They got sealant. We don't want the sealant. They're usually airtight, so we got to be super careful with these. If we get a crack in the seal, can an A&P fix it? No. If we got a leak through the face, no, we can't fix that. That's got to go off to a shop to fix. For shipping, there used to be a whole lab where you take it out of the aircraft and you put it in a box and you pretend you're shipping it to me, the instructor, and then show up and I'd be like, oh, how did they package it? Basically, super sensitive equipment, they would want you to know if it's a gyro and you can cage it, cage the gyro when you ship it. But the other big thing is you want to cap the air ports, right? So if you got air ports coming off the back, any of the air ports you're going to put a cap on. A lot of the ones that we have for all our labs don't have caps because I didn't want to steal all the caps that Matt owns. So make sure when you're shipping instruments you cap them. A lot of times they'll say you put in foam inside a box. Sometimes they'll do foam inside a box, inside a foam, inside a box, if they're super sensitive, because we don't want them banging around. If they're electronic boards, a lot of times we'll put them inside our static bags, anti-static bags, to make sure that the boards don't have any issues when we're shipping. The reason I have this slide is Prepware the FAA has your knowledge and risk sections. Our shipping instruments is you don't just throw them in a garbage bag and throw them down. You gotta make sure the holes are plugged. If it's a sensitive to shock, pack it in foam. It should be stuff that makes sense to you. Alright, markings. That picture's in your book for markings. Either read through it when you do lab or when you get a chance. But basically, we got the different marks that are on there. Green is usually normal, right? Yellow is usually a approved but caution, and red is usually a never exceed. So they have those green, yellow, red for almost everything in there. And that's basically a slide green is good, yellow is caution, red is either a maximum or maybe a minimum. Maybe it's an oil pressure. If you have a red on the bottom, it's a minimum oil pressure. All right, blue and white are for information. Blue and white are for information. So maybe it's a flap speed. Maybe, is there a blue one on here?
Case, sir.
Yeah.
Where's the blue? There we go. Blue radial line, best single engine rate of climb airspeed. Oh, that's another one, yeah. So if you lose an engine, but we still don't want to hit the ground, how fast should we climb in a twin engine? It's a little of a misnomer. It's if I have one engine out of a twin engine, what's my best rate of climb? And they'll say whatever that blue radial line is at. So if you lose an engine in a twin engine, now you're down to single engine. So the best climb rate in that aircraft. Yeah. All right. Somebody said, "Hey, Case." I didn't see.
Yeah, I
it.
was just wondering if you could go back to the previous slide. Yeah, if you just hang out there for a while.
All right. What gauges have two red lines? Anybody? What would your guesses be?
One with 2 gauges on it, a boom gauge.
No. Oil pressure would be one. Yeah. If I get too high oil pressure, that's not good. Too low oil pressure, that wouldn't be good either. What else might be similar?
Fuel pressure?
Hey, you guys are good. Fuel pressure. If my fuel pressure is too low, my engine's not going to run. If it's too high, something's wrong. So fuel and oil, two red lines. There's probably more with two red lines, but that gives you an idea. When they say red line, it's not just max. Sometimes it's min as well. Alright, white line. Oh, white line. I was like, see the white line? What is it? See this white line. Everybody see this white line? It's painted on the outside of the case. It's because they installed some lines on the outside of the case. Or like you guys are going to do, you're going to put some lines on the outside of the case, right? Well, if you were going to put lines on the outside of a case, what if the glass moves? Oh, no. Now all your lines are in the wrong spot. So they call it a slippage mark. It's painted from the glass to the outside. Notice I said painted. It's not stickered, because if it was stickered, well, one side would move, and you wouldn't know if it moved or not. So it's painted. If the glass moves, part of my paint moves. It's kind of like torque seal. It's the same idea of torque seal. So anytime you put markings on the glass on the outside, you will want a slippage mark. So if you want 100% on your lab, better put a slippage mark on there, right? Makes sense? Otherwise, if the glass moves, you got bad lines. As Columbo would say, just one more thing. Yeah. One more thing. With no notes. I don't know what the thing is. Well, that's weird.
Oh, Tony.
All right. I guess you got a half hour because you're not going to really get labs out before cleanup time. But dismissed. Well, what are you going to clean up? However you want to look at it. Yeah, go out in the sunshine, take a 15-minute break. Now we got 5 minutes. All right. The other lectures will be shorter. I had to kind of get through these so you guys can pick away at Lab 1 as we're going over the next couple days. So, yeah, if somebody wanted to adjust the vacuum pressure, you could go to the Lab 5 and look up what aircraft. Somebody wanted to start on gauges.
Or just
It is a bit, it is.
There's one more thing.
I think I've seen that video.
Outside air temperature proposal was the Ford
I feel like it's
fuselage
too
station
Oh, what?
I feel like it's got it has
Yeah, but that's two instruments. Though. Like this one here.
It can be
No,
measured.
I got
and it's
fuel pressure. Yeah.
power.
I see what you're saying, Matthew.
Let me get to that.
Would you, or you have a technical on your diaphragm?
Set up one more time with the picture.
I thought you were like smart.
That one? It's not so right. Doesn't have a what?
Dale Crane.
Don't save.
Located in the heat exchanger ram air duct.
You find that one? Tiki?
Yeah, you just have to
Your
type
right wing stuff.
right wing stuff. Where'd you find right wing stuff? Did I miss something?
Oh, you're right, go back
Oh,
to.
it is right wing stuff. Okay, yeah, I did.
I just like, I kept going through the things until I found it.
Oh, you know what? I can't read well.
This might be a class that I request multiple days extra on.
Yeah.
The thing is, if we did, it'd be more to give you more labs. And when you get all done, it's like, what
If you do it to next year.
what more can you do on labs? You wanna install and remove more instruments. That's why it's a lot of lecture. You're not allowed inside much, so
You don't have to read it upside down.
You
It's
can
so
rotate it.
nice.
It's something, some of it is upside down, but some of it is.
Yeah, look at that. I read
Definitely lecture
paragraphs
heavy.
upside.
I was like,
Just rotate the page.
Well, I didn't want to take my computer.
No,
go like
you
this
can
during
rotate the page.
be
Like
like,
a
we could
something.
make it a longer class and add labs that you don't have to do.
I'm not sure which one it is.
Oh, that's refresh. Oops, sorry. He suggested it, not me. He suggested it, not me. Do not blame me.
Sam doesn't want to ask. He's the tech
else.
Hey, nerd.
rotate the page.
This is why I
Open it up in print.
Yeah,
So
so
you can
Upside
rotate it on
down.
the screen.
just doing that so you can see better. So here's
Oh,
what
wow.
we're running off of that.
It's
to
line
make some
control
put
PDF.
page
This is
numbers
big.
out. I don't even know what I
Could
was.
go to like,
It was important though because I need to reference it.
Also, don't hit F2.
Oh, right.
so we're,
Or F4.
Hit Alt
Um,
so
F4.
it's sucking actually through
Do
the
I get
loader.
no?
Alt F4 is
What
the best.
happens
Through
if
here.
you do that?
So here's the
What
second.
happens?
Great thing.
So basically this guy is measuring
Only the best.
the pressure coming
It'll
into
automatically close whatever window you're working in.
because that's what's coming from the instruments, is it's
Nice.
comparing
It's very
pressure
good.
around it to what's coming into it.
The big red
So that's the
button.
one we adjust.
You on the Chrome?
And it's another,
Heat exchanger.
yeah,
Right.
yeah, if you wanna plug it into the wall.
Oh my gosh, should I see a picture of my cat this
Does
morning?
work, it's crazy.
Not sure. I felt so guilty.
These are
leaving
both
her.
ones, basically low pressure. So one
Look
comes
at her.
That sounds like a
She'll
really
like
good
sleep next to me under the covers and I got up. She's like, why are you leaving me? And I'm like, I'm sorry.
sucking through this instrument, getting here, so.
You okay?
Sunday night, Amanda's dog decided that she was gonna like, and she, it's not that she, no, she hates everybody.